Hello everyone, today I will present a small project where I deploy a web application on Kubernetes. The goal of this project is not only to run an application, but more importantly to understand the core objects inside Kubernetes and how they work together. In this demo, we deploy a simple Node.js web application inside a container. The architecture of this project is very straightforward. It contains three important components. First, the pod, which runs the container. Second, the development, which manages multiple pods and ensures they are running correctly. Third, the service which allows user or other system to access the application. During this project, we will also practice several important Kubernetes tasks. For example, we will learn how to create a development, how to scale the application from one pod to multi-pod, how to perform a rolling update when a new version of the application is released, and how to run back to a previous version if something goes wrong. By the end of this demo, we will have a clear understanding of how Kubernetes manages containers and how developers can deploy applications in a more reliable and scalable way. Problem Kubernetes solved. Before we talk about Kubernetes, it is important to understand the problem it solves. In traditional developments, applications usually run directly on a server. For example, we instance the application, understand dependencies, and then run the application process on that server. This approach works well when the system is small. However, as the application grows, and the number of users increases, several problems begin to appear. The first problem is scaling. If the application receives more traffic, we need to run application instances of the application. Managing these instances manually can quickly become complicated. The second problem is downtime during updates. When we deploy a new version of the application, we often need to stop the old version first and then start the new one. During this process, users may experience downtime. The third problem is container management. Modern applications often use containers, but running many containers across many servers becomes difficult without a proper orchestration system. These challenges are exactly the problem that Kubernetes are designed to solve. Kubernetes solution. This is where Kubernetes comes in. Kubernetes is a container orchestration platform. Its work is to manage containers automatically across multiple machines. Instead of manually starting and stopping containers, Kubernetes handles this operation for us. For example, Kubernetes can automatically start containers when the application is deployed. It can also scale the application. If we more capacity, Kubernetes can run additional containers automatically. Another powerful feature is self-healing. If a container crashes, Kubernetes will detect the failure and automatically restart it. Kubernetes also provides load balancing. When multiple containers are running, Kubernetes distributes traffic across them so that so single container becomes overload. In other words, Kubernetes also developers to focus on building applications. When the platform takes care of infrastructure management and reliability. Project architecture. Now let's look at the architecture of these projects. The architecture is simple but reflects the typical structure of many Kubernetes applications. At the bottom level, we have a POPs. Each POP runs one container that hosts the web application. Above the POPs, we have the deployment. The deployment is responsible for managing the POP. It ensures that the correct number of POPs are always running. In this example, the development will create 3 replicates. This means 3 identical POPs running the same application. At the top layer, we have the service. The service provides network access to the POPs. When a user sends a request to the service forwards that request to one of the POPs. This architecture allows the application to scale easily and remain highly available. Even if one POP fails, the development will create a new one automatically, and the service will continue routing traffic to the remaining POPs. Now let's talk about one of the most important concepts in Kubernetes, the POP. A POP is the smallest deployable unit in Kubernetes. You can think of a POP as a wrapper around one or more containers. In most simple applications, a POP contains only one container. That container runs the application, such as our Node.js web app. However, the POP also provides several important resources to the container. First, the POP provides networking. Each POP receives its own IP address inside the cluster. Second, the POP can provide storage, which allows the container to store or share data. Third, multiple containers inside the same POP can communicate with each other easily. But in many cases, especially in simple applications, one POP runs one container that hosts the application. Understanding POPs is important because almost everything in Kubernetes is built on top of them. Deployment. Managing POPs manually would be very difficult. That is why Kubernetes provides a higher level object called a deployment. A deployment is responsible for managing POPs automatically. For example, we can define the number of replicates we want. If we set replicates to 3, Kubernetes will automatically create 3 POPs. If one of the POPs crashes or stops running, the deployment will immediately create a new POP to replace it. Deployment also supports scaling. We can increase the number of replicates if more traffic arrives. Another important feature is rolling update. We will deploy a new version of the application. Kubernetes will update POPs gradually instead of stopping on POPs at once. This approach ensures that the application remains available during updates. Finally, deployment also supports rollback, which means we can quickly return to a previous version if the new version has problems. service. Finally, we need a way of user or other application to access the POPs. This is the role of a service in Kubernetes. POPs are dynamic. They can be created or destroyed at any time. Their IP address may be also changed because of it directly connecting to POP is not reliable. A service solves this problem by providing a stable network endpoint. The service receives incoming requests and forwards them to the POP behind it. It also performs load balancing, meaning it distributes traffic across multiple POPs evenly. In this project, we use the cluster IP tie-up service. This tie exposes the application inside the Kubernetes cluster. Other services inside the cluster can connect to this service using its stable IP address or DNS name. This makes communication between applications much simpler and more reliable. Our project has 4 flows. User request flow. Let's start with how a user request is processed in Kubernetes. When a user accesses the application, the request does not go directly to a POP. Instead, it first goes to a Kubernetes service. The service provides a stable IP address and acts as an internal load balancer. This is important because POPs are dynamic. They can be created, deleted, or replaced at any time. Their IP addresses may change. The service automatically routes the request to one of the available POP using load balancing. Inside the POP, there is a container running the web application, such as engine, Node.js, or PHP application. The container processes the request and returns the response back to the user. So in summary, the request flow is the user sends a request, the service receives it, the service routes it to a POP, the container processes the request, and finally, the response is returned to the user. Development flow. Now let's look at what happens when a developer updates the application. First, the developer modifies the source code of the application. After that, they build a new Docker image that contains the updated version of the application. Then the developer updates the Kubernetes deployment configuration to see the new image version. The development is responsible for managing the lifecycle of POPs. Once the image version changes, Kubernetes automatically creates new POP running the new container image. At the same time, Kubernetes gradually replaces the old POPs with the new ones. This process is called a rolling update. Because the update happens gradually, the application continues running without interruption. In short, the developer builds a new image, updates the deployment, and Kubernetes automatically creates new POPs with the updated application. Scaling flows. Next, talk about scaling the application. When the application receives more traffic, we may need to run more instances of the application. In Kubernetes, this is very easy. the developer simply run a command like kubectl scale to increase the number of replicates in the development. The developer then updates the design number of pops. Behind the screen, Kubernetes uses a component called a ReplicaSet. The ReplicaSet ensures that the correct number of pops are always running. If a developer scales from 3 replicates to 5, the ReplicaSet will automatically create 2 original pops. These new pops start running containers and immediately become available to receive traffic through the service. This makes scaling application in Kubernetes simple and very powerful. Rollback flow. Finally, let's see what happens if a new deployment causes problems. Sometimes a new application version may contain bugs, unexpected issue. In this situation, Kubernetes allows us to quickly roll back to the previous version. The developer simply runs the command kubectl rollout undo. Kubernetes keeps a history of application version using ReplicaSet. When a rollback is triggered, Kubernetes restores the previous ReplicaSet. The previous ReplicaSet then recreated paths that run the older stable version of the application. Because this process is automated, the system can recover quickly and continue serving users without major disruption. In summary, rollback allows us to safely return to a working version of the application if something goes wrong. In Kubernetes, there are 2 common ways to deploy an application depending on the environment: local development and cloud development. The first way is user mini-queue, which is typically used for local testing. The process is simple. First, we create a Docker image for our application. This image contains the application code and unrequired dependencies. Next, we load the image into mini-queue because the local Kubernetes cluster needs access to that image. Finally, we update the Kubernetes deployment, and Kubernetes will create new pops using the update image. The second way is deploying to the cloud, for example on AWS. These steps are similar but include a registry. First, we create the Docker image. Then we create an image that points to a container registry, such as Amazon Elastic Container Registry. After that, we push the image to the registry so the Kubernetes cluster can access it. Finally, we update the document. Finally, we update the deployment. The Kubernetes will roll out the new version of the application. In short, both approaches follow the same idea. Build the image, make it available to the cluster, and update the deployment. In our project, we use mini-queue. Now let's look at scaling pods in Kubernetes. One of the powerful features of Kubernetes is that it allows us to scale applications very easily. For example, if our application needs to handle more users or higher traffic, we can run the following command. This command tells Kubernetes to scale the deployment to 5 replicates. In other words, Kubernetes will make sure that 5 pods are running for this application. After the command is executed, Kubernetes automatically creates additional pods. So instead of running a single instance, the system will run 5 pods. Each pod runs the same application, allowing the workload to be distributed across multiple instances. This improves both performance and reliability. In summary, Kubernetes makes scaling simple and fast. With just one command, we can quickly adjust our application to handle more traffic when it. Now let's talk about rolling update in Kubernetes. When we want to release a new version of an application, we usually update the container image in the deployment configuration. For example, we may change the image version to version 2. After this change is applied, Kubernetes does not stop the application at once. Instead, Kubernetes performs a rolling update. This means Kubernetes updates the pods gradually, one by one. For example, an old pod running version 1 will be replaced by a new pod running version 2. So the process looks like this. While the new pods are being created, the renaming of pod continue running and serving users. The biggest benefit of this approach is zero downtime. Users can continue using the application normally while the new version is being deployed. In summary, rolling update allows us to deploy new versions safely and smoothly without interrupting the service. Now let's talk about rollback in Kubernetes. When we deploy a new version of an application, sometimes unexpected problems can happen. For example, the new version may contain a bug or it may not work correctly in the production environment. The good thing is that Kubernetes provides a very simple way to fix this situation. If the new version causes an issue, we can run the following command. This command tells Kubernetes to roll back the deployment to the previous stable versions. Kubernetes will automatically stop the problematic pods and recreate the pod using the last working image version. The process is handled safely and gradually, so the application can quickly return to a stable state. This feature is extremely useful in real-world systems because it allows teams to recover from errors very quickly without complicated manual work. In summary, if a new release causes problems, Kubernetes makes it easy to immediately restore the previous version and keep the service running smoothly. Now let's find out the configuration. First, namespace. Let's take a look at the namespace configuration. In Kubernetes, a namespace is used to organize and separate resources inside a cluster. This helps us manage applications more easily, especially when multiple projects or teams and using the same Kubernetes cluster. Here is a simple example of namespace configuration. Let us briefly understand each part of this file. First, API version specifies the version of the Kubernetes API that we are using. For basic resources like namespace, version v1 is commonly used. Second, kind namespace tells Kubernetes that we want to create a namespace resources. Finally, inside the metadata section, we define the name of the namespace. In this example, the name is web app. Once this file is applied to the cluster, Kubernetes will create a new namespace called web app. After that, we can deploy resources such as pods, deployments, and services inside this namespace to keep them logically separated from other applications. Let's look at service configuration. In Kubernetes, a service is used to expose and connect pubs inside the cluster. Since the pub can be created and destroyed dynamically, their IP addresses may change. A service provides a stable endpoint, so all the components can always access the application. Here is the example of a service configuration. Let's break this down step by step. First, API version specifies the API version used for this resource. And kind service tells Kubernetes that we are creating a service. Next, in the metadata section, we define the name of the service as web app service, and we place it inside the web app namespace. Then we move to the spec section, which defines how the session works. The type is cluster IP, which means this service is accessible only inside the Kubernetes cluster. It is commonly used for internal communication between services. Next is the stash selector. The selector tells Kubernetes which pods belong to this service. In this case, it selects pod with the label app web app. Finally, we define the pod configuration. The service is both pod 80 and it forwards the traffic to pod 3000 inside the container. So when another service sends a request to port 80 of this service, the request will be routed to port 300 of the matching port. Let's look at the deployment configuration. In a Kubernetes, a deployment is used to manage and maintain a group of pods. It ensures that the application runs with the designed number of instances and allows us to easily update or scale the application. Here is an example of a deployment configuration. Let's go through the important parts of this file. First, API version. and kind deployment tell Kubernetes that we are creating a deployment resource. Next, in the metadata session, we define the name of the deployment as WebApp deployment, and we play it inside the WebApp namespace. In the spec session, we define how the application should run. The ReplicaSet field tells Kubernetes to maintain 3 pods running at all times. If one pod fails, Kubernetes will automatically create a new one to replace it. Next is the selector, which identifies the pod managed by this deployment using the label app, web app. Then we define the pod template, which describes how each pod should be created. Inside the template, we specify a container named web app that runs the image. The container is pod 3000, which is where the application runs inside the container. Finally, we define resources request and limit. Request specify the minimum resources the container needs, while limit define the maximum CPU and memory it can use. This helps Kubernetes manage resources efficiently across the cluster. Thank you for watching.